he's quite greedy, maybe, but I'm just going to say this. Dave was probably the first person, well, he was the first person I really saw, because I went down to Hurtling and I went from not seeing any flat earthers to all of a sudden seeing about 20. I ran a table, we were going to do an experiment down in Hurtling between there and Brighton. And then I walked into the bar and the very first person I saw that he recognised was this guy. And the other day we come through the airport and they wanted him to go through the scanner. And even though this is Dave's story, so maybe you should say it, I'm going to say it anyway. He actually objected to going through the scanner because of the radiation, and maybe Dave has spent a couple of seconds explaining a little bit more in the depth. But what it is, they were saying that they actually stop people randomly. So I've actually renamed him for this weekend, Randomly Dave.
Hi. I'm Dave, and I'm a flat earther. I've been globe free now for 5 years. Have we got the picture yet?
Is this your presentation on here?
Okay, so I've been doing a little series of videos called Flat Earth 101, where I kind of delve into a particular topic and just like try and cover it comprehensively. So I think the first one was called The Hunt for the Curvature, yeah, and the second one was called The Gravity of Dropity. So this one is actually called The Spinning Orbiting Hurtling Earth. Okay, so I'm going to be talking about Earth's motion. And to go on about what Gary was talking about, whenever I go into an airport, I will not go through their, scan bastard thingy, right? Because not only because of the backscatter radiation that they're sort of dousing you with, which they will tell you, it doesn't harm you in the slightest. Yeah, it's less powerful than your mobile phone. We know how bad the mobile phones are anyway. The main reason that I do not consent to these scanners is because if everybody who in the airport did the same as me, they'd have to get rid of those scanners. Right? So I stand there and I kick up a fuss very loudly. I get the supervisor, the manager out there, and I kick up a fuss. I inevitably end up being groped by the local homosexual. But and I make sure my body language, you touch something you don't. Right? But I make sure they know that I'm not putting up with it. And if one person sees me do that and decides to do the same, hopefully more people would do it, because we're sleepwalking into the end of the world. Seriously, people. I just watched all these sheep behind me just go, and I was told, during this process that from next year or 2021, it's going to be mandatory. You're going to have no choice. Yeah, you are going to have no choice but to be irradiated every time you fly. That's what I'm standing up for. So, right, I'm going to the spinning, orbiting, hurtling Earth. Now, the thing about this whole flat Earth thing is that you've got two opposing views, two absolutely opposite views, but they're identical. Yeah, when you look at them, they're identical. So it's just like this. Yeah, if you look at that, you just glance at that, you can either see the train going into the tunnel or out of it. Yeah? But if you just change your mindset a second, now it's going the other way. Can you see that? That's because you've got very limited information, just a few frames being repeated over and over, and there's no difference between the two. It's just your mindset that's deciding one way or the other, okay? And it's just the same as if you're on a train, and in there's a train next to you, one of the trains starts moving, Now there's a case to be said for, you know, either your train moving or the other train moving, okay? Without some independent outside reference point, there's no way to tell between the two, okay? Now that's the same with the flat earth and the round earth idea, because it's only a philosophy that gives you one view over the other. Yeah, they've given you this idea of, you know, this huge cosmology, and you add that to this idea that, you know, it could go either way, and now you've got a bias towards one and not the other. So I'm going to be, maybe I'll highlight the times when you've got a train situation, okay? So this is my favourite physicist, and I didn't know I had to start this manually.
Now I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we well, don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience. Compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is, it doesn't make a difference how smart you are, who made the guess, or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
So that's it. I mean, that says it all there. If it disagrees with experiment or observation or experience, it's wrong. I say, so kind of keep that in mind as we go through this. This was from George Ellis, who's a famous cosmologist, and it was echoed by Sir Fred Hoyle, who's the Astronomer Royal. He said that I can construct you a spherically symmetrical universe with Earth as its centre, and you cannot disprove it based on observations. Which means that the heliocentric model and the geocentric model are identical. It's another train, okay? They're identical, and it's just philosophy, as I think he says here, using a philosophical approach that you know, distinguishes between the two. Okay. So you can see here are the two models. Now, the heliocentric, okay, is identical to the geocentric. Right? If you focus on the sun there, it moves that. But again, if you focus on the sun in that model, it's exactly the same model. Right? It's just, again, a philosophy that says one is different from the other, but they're the same. So we're told that the motion of the stars is what proves that the Earth is rotating. And this is interesting. This video is from, I think it's like Argentina or somewhere right down on the, at the tip of South America. And you can see it's rotating anti-clockwise, but the centre is way below the horizon, which is what you'd kind of expect. But and in a minute it's going to sort of flip around, the camera's going to move around. And you only catch it for a moment, but any second now it's going to flip around, it's going to change and it's going to turn around and you'll see it rotating, you know, so viewed down to the southern hemisphere. And he said, now, he says, come on. Right. So now the camera's moving and you only catch it for a short amount of time, but again, the axis of rotation is down near the horizon. This is down, you know, way down south. So you only catch it for a second, but it's like down there near the horizon. So how can that be? Because where we are, okay, when you look up at the North Star, it's like up there from where we are, okay? So you should see the same from the southern side. Does that make sense? Yeah, funny that, isn't it? Anyway, so the motion of the stars is what we're told proves that the Earth is rotating. And I've said this before, that, you know, Earth's axis is always seems to be pointing at Polaris, and the 1,000-mile-per-hour spin of the Earth is what's causing the stars to look like they're moving around us. But any small change in Earth's position would mean that the pole would not point to Polaris, which is 2 quadrillion miles away. Okay, so isn't the Earth supposed to be moving around the sun? Yeah, that would constitute a bit of a change. But fair enough. If I'm standing looking at some stars that are 2 quadrillion miles away, if I move in this plane of motion, then the stars wouldn't look like they're moving. You know, just like when you're on a train and there are mountains off in the distance, you know, you can look at the mountains and they'll hardly move. Fair enough. But that's only in one plane of motion. You know, if I was to look at the stars and move in a different plane of motion, well, the stars disappear. Or a different plane of motion, the stars disappear. Right? But here we are. Yes, we're moving in one plane of motion, but the pole is off-center. So you combine those two, you're getting another movement in a different plane of motion. So, I don't know, again, if that makes any sense either. But the sun is also moving. And we're going to have a look at the sun's motion. Now, a lot of you have seen this. Yeah, that the planets are corkscrewing around the sun. So again, imagine that the Earth, one of those planets, is tilted on this plane of motion, right, away, and it's all corkscrewing as well. How can it possibly continue to point to Polaris? But this isn't the whole story. He says, the sun is also corkscrewing through the universe. Yeah? Now, I don't know if you remember, back in 2012, that was supposedly the time the sun moved across the plane of the ecliptic. Does everybody remember that? Oh, come on, wake up. I know it's after lunch. But, so the sun is going up and down. So it can't literally just go up and down. And it can't do a sine wave motion. There's no physics for that. The only thing it can be doing is this corkscrewing motion. Okay? So, how are we getting star trails like this? It's only accounting for one motion. And it's the slowest out of all the other motions. This is impossible from their model. This is what they're also telling us is happening. Yeah? That, you know, it's that the stars are static and it's the Earth moving. Again, this is one of those trains. Yeah? Which one's moving? Okay? But who thinks this is ridiculous? You know? So apparently this is what they're saying is actually happening. But we have some experimental proof that this isn't what's happening. So
I've attached the whole setup to
this is Rob Durham.
the tractor, which I've blue tacked to the table, and I've blue tacked the actual frame to the table as well. So this here is the...
I'll stop you there for a second. He's using a gyroscope. Now a gyroscope has a property called rigidity in space. So once it's set spinning in a particular orientation, it will stay there, regardless of anything, regardless of where it is on Earth, how it's oriented to the centre of the Earth, or whatever. It's rigid in space. Okay. So the idea is, if you set a gyroscope spinning, and you know, you set it down on your tabletop, well, if the Earth is moving round, well, the gyroscope will stay rigid in space and appear to move, you know, because the Earth is apparently moving. Okay, got it? Got it? Yes. Oh, for crying out loud. So I'll just restart, or not restart, carry on.
The angle that we're looking for.
So what we're looking for is this effect.
See how the gyro wants to rotate and stay in the original orientation? Well, that angle that is rotating, that this bar appears to be rotating over the device, that is the angle that we're looking for. That is the angle that we should be able to calculate this gyroscope moving due to the rotation of the Earth underneath us. So without further ado, let's get on to the test. So I've just attached the motor there. It actually takes 4 AA batteries to power it, and I've run this test quite a number of times now and put quite a few batteries through it, so I kind of know how long they're going to last and what sort of
I've
sound
sped up
comes
the
from
actual
motor.
experiment because I think it's important for you to see the whole 6 minutes, so I've sped it up a bit, yeah, so you can see it. It's important to see the whole 6 minutes because, you know, just in case any journalists are in here thinking that I'm, you know, just making up stuff, you've got to see, you know, the whole 6 minutes. But yeah, we'll sped it up.
Let's get up to speed now. We're going to remove the motor and replace it with the piece of Play-Doh to get it perfectly balanced. And now I'm going to demonstrate some precession by gently pressing on the horizontal bar there. And now I'm going to line it up as best I can, so that you cannot see the brass flywheel from above, and it's as sort of straight up and down as possible. So if we just take note of where we are now, you can see a 0 on the top right, just to the right of the bar. You can see a 0 is there. And you'll notice that you cannot see the brass flywheel from above now. So we are sort of dead centre above it. So now it's just a waiting game. So while we wait, let's just have a look at a brief history of the gyroscope. In early times, people discovered the spinning top, a toy with a unique ability to balance upright while rotating rapidly. At the time, sailors relied on sextants for navigation, measuring the angle between specific stars on the horizon. In the 19th century, Fleury created a top that was continuously powered by air gas.
Sorry, I feel I have to show the whole 6 minutes,
the wheel,
you know, sped up,
process
but
that has
there you
been
go.
used for thousands of gyros since.
Just so you see, it's not
The
moving.
first modern gyroscope was
100%.
designed in the early 1800s by Johann Gottlieb Friedrich von Bernberger, a professor at the University of Tübingen in Germany. It was made with a heavy ball instead of a wheel, but since it had no scientific application, it faded into history. In the mid-19th century, the spinning top acquired the name gyroscope, though not through its use as a navigational tool. French scientist Leon Foucault had experimented with a long, heavy pendulum in an attempt to observe the rotation of the Earth. The pendulum was set swinging back and forth along the north-south plane, while the Earth turned beneath it. Foucault corroborated the observation by using a spinning top in a similar manner. He placed a wheel, rotating at high speed, in a supporting ring in such a... So going back to the test, we've exceeded 6 minutes now and there's no observable movement. You can still see the 0 to the right of the bar in its entirety, and you still cannot see the brass flywheel from above. So how much should the gyro have precessed? What angle should the gyro's axis have moved? The calculation is the sine of the latitude times 15 degrees per hour. My current latitude is exactly 53.06 degrees north. So the angle in which the gyro should have moved in 6 minutes is 1.2 degrees. Now this doesn't sound a lot, but let's assume that Leon Foucault's experiments were performed in Paris. He should have seen even less based on his latitude. And let's not forget that he didn't have an electric motor spinning his gyro up to 9,000 RPM.
So one of the proofs out there about the spinning Earth is Foucault's experiments with his gyroscope. A wooden gyroscope that he used a pull string to get going. Okay. Now Rob Durham was using a precision, gyroscope made with top quality brass and perfectly balanced and everything with an electric motor, and yet he couldn't replicate what apparently Foucault discovered, and all this idea is basically based on. Now, how many of you have heard of Airy's failure? Okay, right. Keep your hands up. How many of you actually understand what Airy's failure is about? Put your hands down. And, come on, be honest. Well, I'm going to play it anyway for those who don't know. So, this is one of the first videos I ever watched that kind of pushed me towards flat Earth, because even though this guy Malcolm Bowden doesn't believe in the flat Earth, and he's actually come out against it and everything, he's actually saying that the Earth is stationary, and here's the proof of it.
If a telescope is pointing at a star, and both are stationary, then obviously the light comes straight into the telescope. In 1729, Bradley found that he had to tip his telescope forward very slightly to get a star in the centre of his telescope. It was assumed that this was due to the motion of the Earth around the Sun. Let us assume that the telescope was moving at 5 miles an hour and had to be tipped 5 degrees. This 5-degree tipping, however, could equally be caused by the ether moving at 5 miles an hour, carrying the stars around the Earth. As we see here, the light would be coming in at the same angle, and the telescope would still have to be tipped 5 degrees. So tipping the telescope does not tell us whether it is the starlight moving or the telescope moving. However, there is a simple experiment that can determine whether it was the Earth that was moving or the ether and starlight. All that you had to do was record the tipping required for any particular star, then fill the telescope with water, which greatly slows down the speed of light in the telescope. So here is the moving telescope filled with water, tipped at 5 degrees, and you can see that the starlight does not now reach the eyepiece at the bottom. This is because the starlight moves much more slowly when passing through water. However, if the telescope is tipped further, say 10 degrees, then the starlight will then be visible again in the eyepiece. It has to be tipped further because the light is now slower when in the telescope. But if the starlight is going past the telescope at 5 miles an hour, then when it is filled with water, no further tipping is needed because the light is coming in at 5 degrees anyway. The starlight stays on the same path but is only travelling slower in the water. To recap, if it is the telescope that is moving, then when it is filled with water, it has to be tipped further to see the star. If the telescope is stationary and the starlight drifting past us, then it does not have to be tipped further. In 1871, George Biddle Airy, the Astronomer Royal, performed this experiment. This is a copy from his original report. You can see that the two readings are virtually identical. If it had been the telescope that was moving, Airy expected a figure of 30 seconds of arc. In fact, he only managed to read 0.8 seconds of arc difference.
So, right there is absolute proof that it's the stars that are moving and not the Earth. And this is why it's called Airy's failure, because he failed to discover the Earth's motion. Yeah? But it's a bit of psychological programming, really. So it's called a failure so that people will discount it. And consequently, no scientists ever get told about Airy's failure. Yeah? This is one of those independent viewpoints that, you know, if we go back to the train analogy, it's like seeing a sign on the platform. Where you see the sign, now you know which one's moving. Yeah? So this is one of those independent points of reference. And it's not the only one. There have been several experiments that show that, you know, conclusively that the Earth isn't moving. And the last one, the cosmic background, microwave background radiation, was the subject of a film called The Principle. And I'm just going to play you a section from an interview with Dr. Robert Sungenis, somebody I had a bit of a debate with. But we'll play that one.
If everything is moving, in other words, all the stars in the universe are moving, how could we possibly determine if we are the center of this moving universe?
Over the past decade or so, we have seen out to the very limits of the observable cosmos. We've mapped its largest structure, the cosmic microwave background, the oldest light in the universe according to the standard Big Bang model of cosmology. What we have discovered is shocking.
On the very largest scale, we see a pattern of really big hot and cold spots which line up around a special axis, which has been dubbed the axis of evil. And that's quite puzzling. Why is there a special direction in space?
Well, you know, it's interesting that you asked that, because in 2009 they set up a probe called the Planck probe. He just came back with the results in 2013 in March. I don't know if you heard about it or not.
No.
The European Space Agency set it up in cooperation with NASA. This was the third attempt that they had to nullify the data that they were finding in the cosmic microwave background radiation that permeates the whole universe, that the Earth was in the center of the universe. The first one they set up was in 1990 called the COBE probe. It came back, showed the Earth was in the center. The WMAP was the second one in 2001, came back with the same data. And what they tried to do was say that this was all an error. There was some kind of misreading, or it was, there was contamination in the apparatus or the sky or whatever. So they set up a third probe in 2009, just came back in 2013. Guess what? Same exact results. Same exact results. And what were the interpretations? Well, the Earth has to be in the center of the universe. And we have somebody quoted in our book, Lawrence Krauss of the Arizona State University, who says, yeah, this means we're in the center of the universe.
Let's pick up on that point a bit. And you mentioned that the background radiation, microwave radiation in the universe, supplied data from which it became apparent that the Earth was in fact at the center of a moving universe. Explain why that is so. Why do these data confirm that?
Okay. Well, the Big Bang Theory predicts that there was an explosion 13.7 billion years ago, okay? So if there was an explosion, then that means the explosion had to come out equal on all sides of the sphere. It had to be what they call homogeneous, okay? And that's naturally accepted. It's like homogenized milk.
Sure.
You know, you shake that thing up and you can't see one place from another place. It's all homogenized. And that's what they needed for this Big Bang universe. What they found when they sent these three probes up, yeah, some of it was homogeneous, but it's like having a bowl full of Jell-O with two swords going through the middle of the Jell-O.
What are the swords?
The swords are the orientation of the cosmic microwave background radiation throughout the universe.
Well, what do you mean by the orientation?
Okay, there's hot and cold spots they found. It's not homogeneous. There's hot and cold spots in this microwave background radiation, and if you align all these cold spots, it forms an X through the whole universe.
Unbelievable.
And guess what's in the middle?
Oh, you're kidding.
No.
This is what the data shows.
This is what the data
shows. What mainstream publication recognizes
The
this?
University of Michigan, Dragon Hutterberg, Craig Copey, Glenn Starkman. These are all the guys who have done all the work on this microwave radiation. They read in their papers. They read one in 2004, 2008, 2010, and 2012, and they're reading another one on the Planck probe.
So you're saying these space probes were designed to explain away the X represented by the hot and
They
cold
wanted
spots.
to make sure it wasn't an accident.
Okay, so there were how many probes in total?
3 in 20 years.
And you're saying that all 3 confirmed what then?
That the Earth is in the center of the universe.
On the basis of the hot and cold spots?
Yes.
Whose alignment represents an X.
An X.
And at the center of the X is the Earth.
Right, and they call that X the axis of evil. That was coined.
Scientists call it the axis of evil.
Call it the axis of evil.
So right there, okay, I've just, well, first of all, they tell us, you know, the motion of stars, motion of the universe, you know, proves that we are spinning, okay? Now I've just shown you several experiments that disprove that. And you can bet the scientists don't get to hear about this stuff. You know, if they know about it, they're willfully ignoring it, okay? So let's see what my friend Richard has to say about it.
If it disagrees with experiment, it's wrong.
It's wrong. You know, I've just shown you experiments that, and you know, science is about saying, okay, if we see something that doesn't match up to our model has to go. But they're not following the scientific principle. So, we're told that this is our solar system, okay? And bear in mind, all the measurements and observations seem to confirm this kind of model, yeah? So, you know, when we look through telescopes, all the planets are arrayed along what they call the plane of the ecliptic. So there's like one plane which all the planets go around in. In fact, I think there's 2 planets that don't quite do that, Mercury and I think it's Neptune. One of them, they sort of slightly off. But this generally is what they're saying is going on. So how can this align with that? Okay? Now think about it, yeah? The sun's moving and all the planets are supposedly in that plane of motion, yet they're all moving as like a whole system, a plate. Yeah? So just to think about this a bit further, imagine this scenario. So imagine I've got like a sun on a piece of string, and all these planets are connected by some elastic band, okay? So if I was to pull up on that string, okay, we're told that the speed of gravity is the speed of light, right? Right? Oh, come on! So, according to that, if I started pulling on that piece of string, it would take 3.2 minutes before Mercury would realise something had changed, right? So, and 8 minutes before Earth noticed it, and so on and so on. So you'd get a cone effect. You wouldn't get the plane, you'd get a cone, because they'd take different times to start responding, yeah? So, also, since you've got a pull inwards, if there's motion that way, there'll be motion of the start of the planet inwards. Just like, if you imagine you pulled something up, everything that's connected would start moving towards the centre, wouldn't it? Wouldn't it? Yeah. So eventually, you should get this. You wouldn't get the planets moving in a plane, they'd just be in a string, sort of following the sun. Am I sort of just making this up? I mean, but this is not what we see. This is what makes sense to my mind. Their model doesn't make sense to me.
You've got gravity.
Sorry?
You've got gravity.
Well, that is gravity. I'm just extrapolating what they're saying using the information that they've told us.
Yeah.
They've told us the speed of gravity. They make these graphics showing if the sun disappeared, it would take minutes before the planets would notice it. And I'm just expanding it for what they're telling us is real. So one of the things that I hear often about the rotation of the Earth is that of course you wouldn't feel it because The Earth's only going round, you know, once a day. It's far too slow for you to feel it. Yeah? Anybody else heard that one? Yeah. Well, if you think about it, yeah? If you're on a roundabout, and that roundabout is 8 feet across, yeah, the motion will be 3/16 of an inch every minute. You wouldn't even detect it. You'd have to sit there and look at it and, yeah, I see it, yeah? Okay, so imagine if you sort of widen that to a mile wide, okay? Now you've got roundabout a mile wide. That roundabout, if it was going round once a day, once every 24 hours, would be moving at 2.2 inches a second. So it'd be like this, easily detectable, yeah? Now let's expand it to the width of the Earth, okay? So now it will be moving at 1,037 miles an hour, yeah? 1,521 feet per second. I mean, yes, you would notice it. Contrast that with the gravitron. Anybody been on a gravitron? Yeah? Come on, anyone been on a gravitron? Right, so you know that when that thing goes round, you're like, you know, okay? It only spins at 24 miles an hour. 24 miles an hour, yeah? And sorry, 24. Yeah, 24 revolutions a minute, 37 miles an hour. 37 miles an hour, that's nothing compared to 1,000 miles an hour, yeah? So, but, you know, it's just that they're using this train idea again. It's, you know, you can't test it for yourself. You know, you have to believe what they tell you. This is also what would happen, and I think Iru mentioned this as well. If you spin a ball with water in it, or on it, yeah, the water would collect at the poles. It collects at the equator, and then shoot off at the equator. So, why is there land at the equator? Because if that's the case, if the Earth's spinning at 1,000 miles an hour and only gravity is holding the water to the Earth, the water would still bulge at the equator. So why is there land at the equator? Anybody got an answer? I asked this to Neil deGrasse Tyson, he still hasn't answered me. The other thing that many people would say is, well, if you're on a train and the train's moving at a constant speed, well, of course you won't feel anything because you're moving at a constant speed and it will feel natural to you. You won't even know you're moving. Well, the problem with that is that science tells us that motion in a circle is acceleration in different directions. Yeah? So this is I just took that off of Google. Yeah? The motion of an object in a circle at a constant speed, an object moving in a circle is accelerating. Yeah? So you absolutely do feel acceleration. So let's do a little experiment. Yes? I take it some of you have seen this. Yeah, you know what? I suspect their senses did notice that, you know? So again, Richard, what do you think?
If it disagrees with experiment, it's wrong.
It's wrong! We'll have a quick look at the Coriolis effect. Yeah. Again, Iru talked about this, so I'm not going to sort of go on too long about this. So they tell us that you know, artillery shells, missiles, and all sorts of sniper bullets all get affected by this Coriolis effect. Well, I did a little video a few years ago to show what would happen if snipers had to compensate for the Coriolis effect.
Okay, hold Hold still now. This is where Obama came. Guantanamo Bay, the Patriot Act, and that damn ugly dude you married. Perfect. You're all lined up. Now all I have to do is correct the Coriolis effect. So that's 51.518744 and minus 0.129039. Bearing to target is northwest. Average muzzle velocity? What the?
Hello, Sniper Rifles are us. How can I help you?
Oh, yeah, hi. Could you tell me the average muzzle velocity for a SB-40 sure kill?
That will be in your ballistic table, sir.
No, I don't have my ballistic tables.
Okay, I'll look that up for you.
I'm kind of in a hurry here, so don't put me on...
Oh, please.
Oh, shit. At the
Sir?
Hi.
The average muzzle velocity is 1,024 feet per second.
1,024 feet per second. Thank you.
Is there anything else I can help you with today?
No,
Sure. Have you seen our new line of novelty assassination tools? We're doing a special on exploding toilet seats.
exploding toilet seats? Really? How much? No, that's okay, thank you.
Okay. You have a nice day now.
1,024 feet per second. That's perfect. I have you now, Obama. What? Where'd he go? Shit.
Cool. So, this is again some experimental proof that the Coriolis effect has no effect whatsoever. You know, it's just an idea. This is the Navy's railgun, and it can sight and hit targets 100 miles away. Yeah? It uses a laser to target its target, and then it works out its elevation and fires and hits the target. Now, if you actually sat down and worked out how that does that, then there's no way it could ever hit a target without taking the Coriolis effect into consideration. The fact that it sights it with a laser tells you right there that there is no such thing as a Coriolis effect.
Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles. So imagine you were standing in Texas and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator. That means that the paper airplane is spinning faster as well, and when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right.
So you notice they use the idea of a paper aeroplane and not a real one, because it would obviously apply to a real aeroplane as well. But you don't get planes aiming north to go east. Doesn't happen, does it? So it's rubbish. I was going to say bullshit. I don't think I'm allowed to say that. Right. So I'm going to have to hurry. But right, one of the things we asked is about for helicopters, or we ask, helicopter is hovering. Why doesn't it just sit there and wait for the Earth to spin round it? So they say that the Earth is moving at 1,000 miles an hour this way, and we're going to use the idea of a Harrier jump jet. Yeah. So when a Harrier jump jet is hovering, well, the Earth is moving at 1,000 miles an hour that way. The atmosphere is moving at 1,000 miles an hour that way, and that must mean the Harrier jump jet is also moving 1,000 miles an hour backwards. Yeah, that's their model. Right, fair enough. Okay, let's go with that. So I'm going to look from above. So this is the same sort of graphic, but from above. Okay. So let's imagine now that the jet starts moving at 1,000 miles an hour that way. Okay. According to their model, that jet is stationary now. Okay. So it's overcome its inertia going backwards, and now it's stationary with the Earth moving at 1,000 miles an hour and the atmosphere moving at 1,000 miles an hour. Okay? Everyone with me? Yes. Okay? So, with that, from that point of view, now if that plane turned north, all of a sudden it's going to encounter 1,000 mile an hour winds going this way. Yeah? And this is the only result that can happen. It's again, two models that look identical, but there's a distinguishing feature, and it's the wind speed there that's a distinguishing feature. I'm going to end with this, because apparently I'm under pressure. So I don't know if everyone's seen this. They've now admitted that the moon is in the Earth's atmosphere. Yay! So we didn't really go anywhere special. We could have gone to Basildon, or it's like we didn't. It was still in the Earth's atmosphere. So where did we go? But if you think about it, there was a few problems with this idea. Right? The SR-71 Blackbird, top speed 2,200 miles an hour. Right? But when it goes to that speed, it heats up to 600 degrees Fahrenheit, 300 degrees centigrade. So, if the moon is in the Earth's atmosphere, well, shouldn't it heat up? Even though they say, well, the atmosphere thins out, it will still encounter friction from that air. Which means the moon cannot be in this perfectly balanced situation where it turns at the exact same speed as its rotation. So the face always faces Earth. Yeah, it will start to slow down. Yeah, so how can it maintain that same attitude? It's impossible. Yeah, even the fact that the moon is moving away from us, yeah, means that its orbit is getting bigger, which means it's going to slow down. So it means that the moon should start turning around, so we see the backside of it. Does everybody follow that? Yeah. Right. So again, impossible. I think this is the last thing. This is the last one anyway, so. How everything is moving at the same speed, even when it appears at the horizon, everything is moving at the same speed. That's not what we see in real life. It just means that we're not seeing something that's thousands and thousands of miles across. It's hundreds of yards. Yeah, and ever since we started pointing out this mistake, now they've got the technology a bit better, and now they're putting out newer versions that are right. But they can't get rid of the stuff that they made before, which is wrong. So, you know, we can tell it's all, I'm going to use it, bullshit.
It's wrong.